Today we're looking at Glencoe Accelerated Math Lesson 4.4 on scientific notation. When we look into scientific notation, we're looking at writing either very large or very small values. Scientific notation is called as such because it came out of scientists needing ways to write extremely large or extremely small numbers, such that represented things like the size of an atom or a molecule, or the number of atoms or molecules in some object that could be seen, or talking about something like the distance between planets and between stars. So scientific notation has huge impacts in our sciences. The reason that we use it and we teach it in math class is because it's all about the way that we write numbers. The total value is going to be an estimate when we use scientific notation. We're estimating something. Because when we are talking about the number of miles between Earth and Mars, if we're off by 20 miles, it's okay. If we're talking about the number of, millimeters that the size of an atom is, if we're off by a couple hundredths or thousandths of a millimeter, it's okay. Because when we work with things that are that small or that large, there's what's called margin of error. And that means that the amount that your answer can differ from the actual is much larger. There's a greater margin of error. You can be more wrong and still be within the realm of possibility when we're working with things that super small and that super large. Okay? So scientific notation is an estimate of numbers that are extremely small and extremely large. If we had a number like 42, we're not going to use scientific notation to write 42. But if we were talking about 42,766,876,511, we might. We might. Okay? So, now that we know what scientific notation is, let's look at how we write it. Scientific notation is written as some value x times 10 to some exponent y. So if you see some number, there's one number in front of a decimal point, and then we go from there, times 10 to some exponent, that is scientific notation. The way that we convert between standard notation, which is the way we normally write, and scientific notation, all we're doing is moving decimal places. And as we move decimal places, that changes our exponent that goes with the 10. You're looking at me like I have 4 heads right now. I get it. Scientific notation makes much more sense when we see what it actually looks like with numbers. So let's do that. On page 153, let's look at example 1b, where it says 6.8 times 10 to the 5th. .8 times 10 to the 5th. Is this number going to be larger than 1 or somewhere between 0 and 1?
Larger.
It's going to be larger than 1. How do we know that it is larger than 1? Yes, ma'am. Because a 10 has an exponent of 5. If we have a positive exponent, that means that we have a large number. Correct? Okay, so what we're going to do, we have 6.8. We're going to multiply it by 10 times 10 times 10 times 10 times 10 times 10 times 10. 5 times. So we're going to move that decimal point 5 times to the right to make our number bigger. 1, 2, 3, 4, 5. So our decimal point will end up here. So instead of having 6.8 times 10 to the 5th, that value is 680 680,000. If you're watching this at home, I'm sorry I'm having camera issues today. Okay, so we end up with 680,000. I'm sorry? That's it. We're just moving decimal places. That's all that we have to do to convert from scientific notation to standard notation. We moved 1, 2, 3, 4, 5 times because we had one decimal place behind our decimal point. That means that we needed to add 4 more zeros. Check in the book, am I right? Yeah? Yes, ma'am.
What would it look like if it was a billion?
Just 1 billion?
Yeah.
Okay. In scientific notation or standard notation? Okay. So 1 billion. Okay, so I've got 1. Then I need to add zeros. That would be 100, 1,000, 10,000, 100,000, million, 10 million, 100 million, billion. Okay? So that would be 1. I wish my bank looked like that too. Okay? So this is 1 billion. If I write this in scientific notation, I'm going to have a 1. I do not need to put a decimal point and a 0. 1 times 10. And my decimal point got moved from here. 1, 2, 3, 4, 5, 6, 7, 8, 9. It would go there. 1 times 10 to the 9th power. Yes, sir. Okay, can we take care of it after the lesson? Yeah? Okay. So that would be 1 billion in scientific notation. Let's look at what, I want to go back to example 1C, because there we have a negative exponent. And with example 1C, we're given 3.25 times 10 to the negative 4. If we start out with this problem, our negative exponents, those became fractions with a positive exponent, correct?
Yes, ma'am.
Okay, so then is this value going to be larger than 1 or somewhere between 0 and 1?
Somewhere between 0 and 1.
It's going to be somewhere between 0 and 1. But we're going to write it as a decimal instead of as a fraction. Okay? If we moved here and our decimal point moved to the right, if I have a negative exponent, which way is my decimal point going to move?
Left.
It's going to move to the left. So I'm going to give myself some space. I'm going to have 3.25, and it needs to move to the left 4 spaces. 1, 2, 3, 4. 1, 2, 3. So 3.25 times negative 4 is actually 0.000325. If I have to write out numbers, this is much easier to write than this. Because if we have to write this out all the time, is it likely that we're going to forget a 0?
Yep.
And will forgetting a 0 change our value?
Yes.
Absolutely. We don't want to do that. So, when we're talking about numbers this small and this large, if we round a little bit, it's okay. Yes, ma'am.
So, what I'm seeing is like you put the 4 zeros that you would put that this number you have up there,
Uh-huh.
but you put it in front of the number and you moved the decimal back.
So when we have a positive exponent, we're adding zeros behind. With the negative exponent, we're adding zeros in front. Okay? Alright, now let's look at what we're going to do if we were going to convert from standard notation to scientific notation. Because here we went from scientific to standard. We need to know how to go from standard back to scientific. Okay? Do I need to change my colors up? Are we getting a little tired of the black?
Yeah.
Yeah?
I think
Okay.
we should do like
It's
a
boring.
pinkish, orangish color.
Okay, I can use this color. Some of the colors don't show up on the videos. So, I'm looking at example 2. Example 2A. Example 2A gives us a 4 with 6 zeros behind it. How do I say that number?
4 million.
4 million.
Good. So, if I have 4 million, and I'm going to write that in scientific notation, I need one number in front of my decimal point. I have the invisible decimal point here. It's going to get moved 1, 2, 3, 4, 5, 6 places and go here. Do I need the 4.0?
No.
No. No, I'm going to just write a 4. Times 10. What's my exponent going to be?
6.
6.
Why is it 6?
Because there's 6 zeros.
0.
Not 6 zeros.
We moved over 6 places.
We moved 6 places. Okay? Because if this had been 4,230,000, we could have 4.23, and it would still be times 10 to the 6th, even though we didn't have 6 zeros. Okay? All right, let's look at example 2B. Actually, we're going to do 2C under the got it section. I'm changing my mind. It happens, I'm allowed. Example 2C, and I'm going to bring the book over to make sure that I write it correctly. 0.0000064. Okay. I need to write this in scientific notation. So, I need to take this decimal point and move it until there is one number in front of the decimal point. 1, 2, 3, 4, 5. That would be 6.4.
5.
Times 10.
Hold it. Where are you guys saying 5? Are you guys trying to give me the exponent already?
Yeah.
We're not there yet!
Times 10.
That was a mini hissy fit because I can.
Is that going in the video?
Yes, it did. When we move our decimal point, we end up with 6.4. We have to multiply that by 10 to what power?
-5.
Negative 5.
Oh.
Okay. Why is the exponent -5, not +5? Yes, ma'am.
Because the zeros was in front of the 64.
Because the zeros were in front of the 64. Well, can I put zeros in front of this 4?
Yeah, you can.
No.
But it wouldn't make a difference because 0 has no.
Because zeros in front there don't mean anything?
Yeah, so that's still 4 million.
Okay? Yes, ma'am?
Because you moved the decimal point to the right.
Because I moved to the right instead of to the left. Okay? The direction that we move our decimal point is what determines whether it's positive or negative. Here, and whether our exponent is positive or negative here, tells us whether we're moving to the right or to the left. So, that positive or negative, that determines direction. Okay? That's the other thing, that we can use it as a check to think. If this number is between 0 and 1, it's a fraction. This gives us a fraction. This number is greater than 1. A positive exponent gives us something greater than 1. Okay? So, we need to make sure that those things, we can use it as a check to make sure that our answer matches our problem. Okay? Yes, no, maybe?
Yes.
Fantastic. Yes, ma'am.
So if you have to move the decimal to where it's to where there's one number before it, it's going to be a negative?
So regardless, we're moving our decimal point so that there is one number in front of a decimal point. This has an invisible decimal point, right? So there's one number in front of the decimal, and then you can have as many behind as you want. A lot of times we will we'll stop after 2 or 3, or if we are looking at a number greater than 1, it'll say, then, round to the nearest 10th or the nearest 100th. So it'll tell you how many decimal places to round to. If there are non-zero values in all of these, you're not going to write out the whole thing. That doesn't make any sense. We're doing this to make it easier to write these very large and very small numbers. Okay? Yes, sir?
You can use a calculator and make sure you're right, can't you?
Yes. You can. I don't want to show you guys how to do that quite yet.
Why not?
Because otherwise the calculator did the learning for you.
That's the point I was trying.
No, a calculator is a tool to help you calculate.
And to give you the answer.
A calculator is not a learn for you tool.
I want to look up the calculator so bad.
What? Okay. There is one more thing that we have to be able to do with scientific notation. And that is order values. We have to be able to tell what is larger, what is smaller, based on numbers written in scientific notation. Okay, if we're working with very large numbers, and we had something like 4 million and a billion, we know that a billion is larger because it has more commas, right?
More zeros.
More zeros, more commas. If these were non-zero values, it has more commas, it's bigger.
Yeah.
Okay? We know that with our very small numbers, the further out you go, the smaller the number is. Okay? What if we want to do this from the point of scientific notation? How can we look at the same thing when we don't have commas and we don't have zeros in front of a number for our decimal? How can we still do the same thing? We could take them and put them into standard form, but that might take a while. Look at example 5, please. Example 5 on page 155. And that tells us that we need to put in order from oldest to youngest are geologic time periods. So I told you that we use scientific notation in science. Here we're talking about geologic time. We're talking about time before people could write down what was happening. Okay? It's a really, really, really long time ago. So, what we do is we look at our exponents first. If we're looking at the number of years, years are going to have to be somewhere between 0 and years are going to have to be greater than 1, correct?
Yeah.
If we're talking about geologic time, we're not talking about parts of a day that are so small we need scientific notation for them. We're talking about years and years and years and years and years. So, if I want the oldest time period, that would mean that I have the most commas, I have the most decimal places in my years. Look at the table there. What's our highest exponent? 8. So something's written in scientific notation and we have an exponent of 8. That's going to be much older than anything with an exponent of 7 or 6 or 5 or 4 or 3, correct? Yes? Okay. So then that would tell us that what period is the oldest. Oh, but wait. There are 3 that have an exponent of 8. So we have the Jurassic, the Silurian, and the Triassic period that all have an exponent of 8. So what can we look at to figure out What's the oldest? Yes, ma'am. Look at the whole number next. We have a 2, a 4, and a 2. So what's the oldest?
4.
Which is the Silurian time period. So the Silurian time period is the oldest. We got that one knocked off. Okay? Then what about the Jurassic and the Triassic? 2.45. Is that greater than or less than the 2.8? Greater than. 2.45 is greater than 2.08. And if they're both taken and multiplied by 10 to the 8th power, that's 245 compared to 208 with zeros behind it. The 245 is going to be older because it is greater. So that means we have the Silurian, then the Triassic, then the Jurassic, and our Tertiary would be the youngest. If we are talking about geologic time, we're still talking about 6.64 times 10 to the 7th years. Okay? We're not talking about anything that's recently decomposing like pumpkins on our front porches. Okay? We're talking about millions of years. Okay? So just like that, if we're talking about these time periods, if we're off by 20 years, does it matter?
No.
No. We can round. Absolutely, we can round. Yes. All right. Are there any questions about scientific notation? Yes, ma'am.
Can we just estimate and not have to do any of the work and then round?
No.
No.
No. Because we're not actually changing the values that were given. We're just writing it in a different way. And when we rewrite it, we're writing the estimate. We're writing the rounded value. Okay? You won't be given anything where we're told to round to estimate using scientific notation.
Okay.
All right? Any other questions?
No, ma'am.
Fantastic.